All right, so welcome back. Sorry for the technical difficulties on Monday, but I'd like to pick up where we left off and finish that exercise as finishing to the loops module. So just to remind ourselves here what we were doing, a loan, you take out a loan for a certain amount of principal, and you have to pay the bank a certain a rate, right? And usually that's given as an annual percentage rate, say 5% in this case, but it's computed monthly because you make monthly payments on it. So the monthly rate is, the annual rate divided by 12. N is the number of periods, months in a loan, and so that gives you, so if I say that it's going to be for 5 years, that means 5 times 12, that's going to be 60 months total. And as an example here, we've got, once we plug all those things into that, into this formula here, we get for a $10,000 loan over 5 years at 5%, that monthly we're going to be paying $188.71. We left it off with computing that monthly payment and then using the round function to round it to the nearest cent. Remember that there's these fractions of a cent that we don't want to deal with because you can't pay a half a cent or a quarter of a cent or something like that each month. Now, the way that we accomplish that is by shifting it over, by floating that floating point number over, so that when we use the round function, it rounds to the nearest whole number. Then we correct for it by dividing it by 100. Now, note here that I've used 100 and 100. Do we have to worry about integer truncation here? Monthly payment, that's a double, right? That's declared right here. Monthly payment is a double, so this is going to remain a double. And what about the round function? If I read the man pages, RTM it, if I read all about the round function, right, then I see that it takes a double and it returns a double. So do I have integer truncation issues here? Nope. So we can move on. Let's go ahead and make sure that this actually works. Remember that you use the -lm flag to bring in the math library for this POW function. And when I run it, I'm going to jump up to the top here, and you can see that the monthly payment is exactly $188.71. If you want to, we can expand this out and print, let's say, 10 decimal places, right? And you can see, oops, there we go. And you can see that it is indeed rounded to the nearest cent here. A bunch of zeros afterwards. We're going to want to make sure that we round most of these things to the nearest cent, because when I make a monthly payment, or when I compute a monthly interest on this, then I want to make sure that I'm rounding that to the nearest cent. Okay? All right, so all we're doing right now is printing the months, 1 up to 60 in this case. And again, these are all provided as command line arguments. There's a test case, $10,000 at 5% interest over 5 years. Okay? All right, what's my next step here? So I'm in a particular month. I need to compute that month's interest. So let's go ahead and create a variable to do that. Oops. And make sure that your indentation is all correct. So month's interest, right, is equal to, how do I compute that monthly interest? It's going to be the annual rate, which I called annual rate up here, who would have thought, divided by 12, times whatever the current balance is. Now, would it be correct to multiply it by the principal, right? The principal is the original loan amount, $10,000. But as you pay it down, that principal, that balance goes down, right? After the first month, you pay $147.04. It goes down to $9,852, right? Eventually, you pay this loan off. So do I want the original principal, $10,000, $10,000, $10,000 for each loop? Nope. I want the current balance. Do you see a variable for balance? Nope. Then make one. Right? So double balance. What do we initialize it to? By the way, if I just leave it like this, what value does balance have right now? Big question mark, right? Who knows? It could be 0. 99 times out of 100 it will be 0. But it's that one time that it's not 0 that you need to make sure that you're initializing it correctly. Right? Initially, what will it be in this case? Not 0, of course. It'll be the principal, whatever you started out with. I borrowed $10,000, so my current balance in the first month is going to be $10,000. In the second month, it goes down. Third month, it goes down again, etc., until we get down to 0. All right, so there's the month's interest. And instead of multiplying it by the principal, I'm going to multiply it by the balance, the current balance. In fact, if you want to go back, you can go ahead and call that what it is, current balance. Right? But balance is good enough, right? Because we're actually going to be updating it. So that's the month's interest, right? That would be $41.67. How do I compute how much goes to the principal to pay down the loan? It's going to be the monthly payment, $188, minus $41.67 to give me how much goes to the actual principal. All right? So let's create another variable to do that. Double to principal. Right? And that's going to be the monthly or monthly payment minus whatever you had to pay for interest. So month's interest. All right? Now, be careful here. Month's interest. What did I say that we had to do to that? So that's the month's interest could be, I mean, ideally, it's going to be $47.67. But it could be $47.67 and some fractions of a cent. In fact, if I just look at the way that I computed this, annual rate times 12, or divided by 12 times balance, then what would that look like from a calculator point of view? If you're not familiar with it, wolframalpha.com is an excellent online calculator. It does calculus, it does algebra, it does anything that you want, including basic arithmetic. So 0.05 divided by 12 times 10,000, right? Is that $41.67? Nope. It's $47.66 and then 2/3 of a cent. So is that going to be correct in my program? Nope. So how do I make it correct in my program? I need to round it. Round whatever this was, and of course times 100 divided by 100. Okay? Seems like I'm doing that now a lot. I've rounded here to the nearest cent here, and I've rounded to the nearest cent here, and I've had to repeat a lot of code. If you're repeating code, that should be a huge red flag that you should be doing something else. That something else is writing a function, which is what we're going to do next. Okay? But for now, we'll leave it like this. So I've got most of everything that I need here. I've got the current balance. I've got the amount that I pay to interest in that month. I've got the amount that I pay to my principal in that month. And then I've got the new balance right here. So let's create yet one more variable, double new balance. The new balance is going to be the old balance minus however much you've put towards that principal. All right? Now let's print all of these things together. There's all dollar figures, so %.2f, right? Or dollar sign $0.2f, dollar sign $0.2f, dollar sign $0.2f. How many things do I want to print? 1, 2, 3, 4. Okay. 1, 2, 3, 4. I'm going to be printing the month, the balance, the balance, the interest, so month's interest, and to principal, and finally the new balance. There we go. So let's see if this works now. I'm going to have to, of course, recompile it and run it. All right. Okay, so it certainly runs for 60 months, but does that look correct to you? The same number over and over and over and over again? Nope. What did I fail to do? The first line is absolutely correct. That's spot on if you take a look at this over here, right? I never updated the balance. I computed the new balance, but I've still got the old balance, and that's what keeps computing. The old balance, I still owe $10,000, $10,000, right? I'm sure that banks would love that, and loan sharks would certainly love that. But no, that's not how it works, right? So what's the new? I need to update the old balance. The old balance is going to be, or the current balance, I should say, is going to be the new balance, setting me up for the next iteration of this for loop. Okay? Now let's check it out and see if it works. So the first couple of months are almost dead on, right? In fact, they should be dead on. 985296. Yep. Month 6, I'm going to be left with 9108.50, 9108.50. It looks correct to me. Except that if I look all the way down here at the bottom, after the 60th month, I still owe 14 cents. Now, in real life, a bank might actually forgive this and say, if the balance is less than $1, we're not going to worry about it. Here's the title to your car, right? But maybe a bank does care about that last 14 cents. So how should we take care of it if we need to take care of it specially in our program? Oftentimes, you'll need to deal with an off by 1 error, when the last iteration needs to be dealt with differently, or the first iteration needs to be dealt with differently. You can restructure your loop to do that, or you can just handle it separately. You can have a big if statement inside your loop. If it's not the first iteration, then handle it this way. If it is the first iteration or the last iteration or whatever, handle it this way. Or in this case, I can just stop short, right? Don't do that last month. Don't go up to less than or equal to 60 months. Just go up to the last month and then handle the last month here. Right? Now, if I haven't written the code to do that here, but you'll see now that it will only go up till month 59. Right? Now, here's something that all good programmers do. They put in a to-do. Right? What is a to-do? A to-do is something, I don't want to do it right now. I don't want to have to worry about thinking about that right now. I want to solve this problem over here. But don't forget about that you still have to do that thing over there. So in a comment, you have in caps here, to do, and then a note to yourself on something that you still need to do. So that when you come back, you can remind yourself, oh yeah, I still have to write that one piece of code. For our purposes, I'm going to leave that as a to-do for you, right? I will go ahead and make sure that you've got this in the notes, but otherwise, I'm going to leave that as an exercise for you to finish on your own. Okay. Besides, it's going to be very, very similar to what you're going to be doing in your hack tomorrow. Right? Instead of a loan and paying back money to the bank, you are paying money into your own account and earning interest, and of course, it's being eaten by inflation for a 401k savings plan. Right? Questions on loops? No? Okay. Well then, again, let's go back over here and observe that I did that round to cents kind of thing where I had to shift it by 100, call the round function, and then shift it back. It would have been a lot easier if I had a function to do that for me, right? Does the math library have a round to cents function? No? Well, then why don't we write our own? Right? And that's the whole purpose of writing functions. Let me go ahead and get rid of this and bring in our next topic, right? Functions. All right, here we go. Just a second. There we go. All right. So what is a function in the context of code? A function is a reusable unit of code that may take inputs and may produce an output, right? Now, you've heard of the term function before from mathematics, right? If I write f of x is equal to x squared, then identify. First of all, what's the name of this function? Math folks, tell me what the name of this function is. F, right? Mathematicians aren't that creative. They call their functions f, h, g, whatever, right? That's not what we do in coding. You don't call functions f, because if you call the function f, there's only one function that can be called f, and what the heck does it do? Does it compute x squared? Who knows, right? But in the context of math, what is the input to this function? The input is x, right? What is the output? You usually label it as y, x squared, right? Y is equal to x squared. So this is very familiar. In mathematics, you use a parentheses to denote the input, right? Where have you seen that before in your code? You call the square root function, what do? You put parentheses on it, right? We just took that from math, right? But of course, we call our function something different. In math, you can also have multivariate inputs, right? You can have f of x, y, right? And then you've got a two-dimensional function, or it's mapping in 3D. You can have f of x, y, and z. You can have a function that doesn't take any inputs in math. What would it look like? And the Cartesian plane, x, y, no inputs. In other words, it doesn't depend on x. It always has the same value. It would look like a horizontal line, like f of x, f of nothing is equal to 5, right? You're ignoring the input. And you can have that in code too. You can have a function that doesn't take any input. It's not that useful. You can have a function that doesn't produce output, right? Those are called void functions, and we'll talk about those later. You've already seen a lot of these. Sine, square root, pow, printf, main. Those are all functions. All of them with a descriptive name. They're not called f, they're not called g, they're not called h. The reason that you want to use functions is for code reuse. How many of you would be jazzed about the prospect of having to write your own sine function? Or your own square root function? Right? Nope. Functions facilitate code reuse. Once somebody writes a function to do something, you don't have to copy pasta the code that does that something. You don't have to cut and paste code. Instead, you can just put that code into a function and don't worry about it anymore. It's there for you to use and reuse. And it also facilitates what's called procedural abstraction. So I'm just going to demonstrate this with an idea here. How does the square root function work? Or, you know what? I'm going to change this to, how does the sine function work? How do you compute sine? Suppose that you lived in a world without the math library. Suppose you lived in a world without that TI-82 sine button, right? Or your sine button was broken. How would you end up computing the sine function? Calc folks, what? Yeah. Oh, okay, go ahead. A Taylor series, right? Taylor series? What the heck is that? Don't worry, we're not going to get into it. What's another way? Does anybody know of another way? So the guess and check kind of way. It's numerical interpolation, right? Or something else, right? Who knows, right? Who cares, right? You simply want to use the functionality. Have you ever worried about how the square root function on your TI-80, whatever it is, TI-80 works? No. You just care that it gave you the answer. Likewise, we don't have to worry about how these functions work, these procedures work. We're abstracted away from that. It just does work, right? The functionality is encapsulated. So there's another vocab word. Inside the function, and we don't have to worry about the details. Right? Our purpose is solving another problem. We're computing roots of a quadratic equation or something like that. I shouldn't have to worry about how does the square root function work, how does multiplication work, how do all these other things work at the same time. I should be able to focus on my problem that I'm trying to solve right now, right? Using functions allows you to do this, right? Using and defining functions allows you to reduce your cognitive load, right? So what is a cognitive load? The number of things that you got to keep in your mind at the same time. All those ideas that you have to juggle at one time, right? You can reduce your cognitive load if you are juggling 5 balls in the air. Go ahead and put 4 of them down and focus on that one ball. It is way easier to juggle one ball by throwing it up and catching it than juggling 5 balls, unless you're really good at juggling, I guess. All right. And of course, another great reason to use functions is that standard libraries, external libraries, they all provide useful functionality that have a lot of testing, a lot of debugging, and a lot of optimization behind them. Use them. You cannot hope to replicate those thousands and thousands of man hours that have gone and computing hours that have gone into developing those things, testing them, and optimizing them. Right? You will never beat the standard math library's square root function. Right? There might be occasions where you want to roll your own or create your own function to do something, but those are the exception, right? We don't want to have to do that too often, right? We don't want to reinvent the wheel. We want to use an off-the-shelf solution. When you are problem solving, what is the first question you should ask yourself? Here's a problem. What's the question? What's the question you should ask yourself? I heard it. Is it somebody else to already do the work? Because now I don't have to, right? Excellent. Use an off-the-shelf solution. If there are any Mech-E people in here, right? If you're designing a machine, you don't, this machine is going to need a motor, right? You don't say, all right, well, put everything on hold. We need to design a motor first, right? No, you pull an off-the-shelf solution motor that's already been designed, built, and mass-produced. And then you put it into your machine, right? Don't reinvent the wheel. Use an existing off-the-shelf solution whenever possible, okay? So when we don't have a solution, we have to roll our own, we have to create our own solution. And when we do that in C, let me give myself some more room here, sorry. There we go. That should bump it up, there. As with variables, functions in C have to be declared before they can be used, all right? The way that you do this in C, you declare a function by creating what's called a prototype. Now, this is not like the prototype that you would create, your first iteration of a machine and then test it out, see how it works or something like that. A prototype in the context of code, in the context of C, is a function signature. So a prototype in C is a function's signature. So what is a signature in real life? If I sign something, if I sign a contract, if I sign a loan document, what am I doing? I'm identifying myself. A signature is a way of identifying a function. What function are you talking about? Well, how do we identify a function? How do you, first thing you need is its name, right? A signature consists of the name of the function called an identifier. Right? It also consists of all the parameters. A list of inputs called parameters or arguments. Right? This includes both the number of arguments. Remember, even in math, you can have one argument. You can have two variable inputs. You can have three. You can have four. You can have five. You can have as many inputs as you want to a function. Likewise in C and in programming, you can have as many inputs to the function as you want, including zero, nothing, right? And their type, right? So in other words, does it take a double, or does it take an integer, or does it take a character, right? And which one is which? Right? And finally, the return variable, or return variable type, right? We use the keyword return inside the function to denote this. Right? So as an example, let's go ahead and design a function to compute or to round a number to the nearest cent. Right? And for that, I'm just going to go back to our old program over here. Okay. So let's go ahead and go up to the top here, and I'll explain why we're going to do this before the main. Hint, we have to declare a function before we can use it. All right, so I want a function to round to the nearest cent. What should I call that function? Round to cents, okay. Do what it says on the box, right? Round to cents. Right. Now, can I use spaces in variable names? No. Nope. So I can't use spaces in function names either. Instead, I'll use the same casing convention that we use for variables, lower camel casing, round to cents. Now, in general, you want your variables to be nouns, right? Number of students, principal, annual rate, monthly rate, right? You want your functions, they do things. So in grammar, what do we call those words that do things? Verbs. So we want generally you'll want to name your functions after verbs. Round to sense, that's a verb, right? It does something. Right? So that's the identifier. We also need a list of inputs called its parameters and their type. So if I'm going to round a single number, then I need a single number as input, and I also need to define its type. I'm going to take a double, x, and I'm going to return a double, rounded to the nearest cent. X. That sounds really mathy to me, f of x. Is that a great variable name? No. What does it represent? Money, currency, dollars, amount. Right? These are all great names. Let's choose one. Okay, so it's already cents, but I'm rounding it to cents. That doesn't sound right. Dollars? Dollars is just whole dollars, right? Dollars and cents, that's the currency, right? So currency? Are all currencies do all currencies have a one cents in them? No. USD for US dollars. Avoid acronyms, avoid abbreviations. Did everybody look at that and immediately think US dollars? Okay, maybe you did, but would everybody, if you took this out of the context, would you know USD? What USDA? What is that? Right? I'm just going to go ahead and go with amount. Right? Now, we could have gone back and forth all day. Right? There's an old saying in computer science that in computer science there are only two difficult things. One of them is cache invalidation, and the other is naming things. Right? So you could argue all day and go back and forth. Well, I think it should be amount. I think it should be US dollar. Make a decision and stick with it and move on. Right? Don't worry about it. Right? As long as it's descriptive, as long as it's understandable, you can always go back and refactor it, rename it to if it's unclear. Right? If you show your code to a colleague or a peer or whatever, and they go, "What the hell were you writing?" Right? Okay, well that represents US dollars. Okay, well amount would be okay, right? Something like that. Right? Now the third thing that we need is the return variable type. This is going to end up returning the double because it's not going to return an integer, right? We're gonna round this to $188.71, not $188, right? So there is my prototype. How did I end it? With a semicolon, just like I end a variable declaration with a semicolon, right? So it ends with a semicolon, and that's necessary. I've just declared that there is this function called round to cents that takes one input of type double and returns a type double. Right? What does it do? You say what? It doesn't do anything yet, so we haven't defined what it does yet. But what is it supposed to do? Round to cents. So let's document that. Right? And it's going to be pretty simple because it's obvious what it does from the name, and it's only going to be a one-liner anyway. But this function rounds the given amount to the nearest cent. And if we want to be really, really, condescending, we could say nearest 100th decimal place, right? And returns the rounded result. Right, there we go. You don't need to write an entire essay on rounding, right? One simple sentence is enough. But for every function you write, you need documentation like this. And it's a good idea to start getting into the habit of using doc-style documentation. /** followed by a vertical line of stars and then ending it right here. Right? It's just a good habit to start getting into because every language supports doc-style comments like this. And they've got tools where you can just run this tool really quick and generate all these pages of documentation if they're all in the correct format. Okay? All right? Great. Now, once we've got our prototype, we can use it. So round to cents. Instead of multiplying by 100, what I can do is I can say round to cents. That monthly payment. That looks a whole lot cleaner now, right? Round, it doesn't do anything yet, right? But that's okay. An integer doesn't do anything, but I can still use it, right? And get rid of this, and get rid of this. Right? There we go. It does, you're right, it doesn't do anything yet. And in fact, the compiler is going to tell me that. Wait a second. Round to cents? Yeah, I know what that is. It's this function that takes a double and returns a double. And I know that its name is round to cents. And I see that you're using it here. Great. But I'm not able to link into that function because I don't see a definition of what it does. This is the exact same error as if we had left off the LM flag. Right? Now we get undefined reference to round to cents and undefined reference to POW. Right? It needs to know, where the hell is this thing? Right? Is it in the math library? Is it in another library entirely? Right? We'll get to that eventually. But for now, what we're going to do is we're going to put the definition down below. Right? So let's note this. Right? After you have a prototype, you can use the function. But the prototype does not, emphasize that, not define what the function actually does. Right? So what you need to do is you now need to provide a function definition. The function prototype is just its signature. Like, what's its name, its input, and its output types. Right? The actual definition involves repeating the signature. The definition repeats the signature and then provides a function body, right? Surrounded by curly brackets. Right? Okay? So let's do that down here. Get rid of that. There we go. I'm going to cheat and cut and paste, copy pasta, right? And come down here and put it right here. I've just violated a sacrosanct rule of coding, the DRY principle, the don't repeat yourself principle. Do you see this right here? This is documentation, right? This is also documentation. Should I have two copies? No. Nope. Don't repeat yourself. Write once and that's it. So get rid of documentation on the definition. The documentation belongs with the prototypes, okay? And it should not be repeated. So let's note that. Documentation belongs, is required, and belongs, it's not required syntactically, it's required for the course, belongs on the prototype, not the definition. Don't repeat yourself. DRY is the don't repeat, can't type today, yourself, right? The DRY principle, right? And it's also why we write functions to begin with, right? Don't repeat yourself by shifting over by 100, calling the round function, and then dividing by 100, right? Don't repeat that 5 times. Put it into a function, call that function instead, okay? All right, so with a function definition, we don't have the semicolon. Instead, we have the function body. Whatever we put inside these curly brackets, that's what happens when the function is called. So what do we want to have happen? We want to compute a result, right? That's going to be a call to the round function of the amount times 100, shifting it over, and then once we've rounded it to the nearest cent, shift it back over. Right? And then finally, ultimately, return that result to whoever called me. Invoking a function, calling a function, that's when we actually, call the function, just like square root or POW, or like we use POW over here. We called that function. We invoked that function ran its code, whatever code was inside of it, right? We're invoking the function right here. We're calling the function. The function gets called. It starts executing its code. Well, it has to go back to where you called it and return a result that can then be stored into a variable, monthly payment in this case, right? Or down here, month's interest, right? The return keyword here is returning the result, right? Now, in this particular example, I've created a result, a variable called result. The result variable, in this case, is what's called a local variable. And we'll go over this in more detail later on. That only exists inside this function. And I'm going to prove it to you. First of all, let's go ahead and compile that. And we can see that it works just as before. Exact same behavior as before, but now it's a little bit cleaner because we're offloading some of this cognitive load of how do we round a sense. We put that into a function so we don't have to worry about that anymore, right? But what about this variable result? Up here in this main function, do you see any variables called result? Nope. Let's try to print result. Printf, result is equal to %d, or f, I guess, result. Is this going to compile? Nope. It doesn't know anything about result. Result is a variable that exists in this function. It does not exist in the main function. Functions have segregation of variables, that they have a scope unto themselves. If you create a variable inside of a function, like say monthly payment, we created that inside main. Would you expect to be able to do anything with monthly payment down here? Nope. It belongs in that function up there. The result belongs in this function down here. So it is local to that function. Go ahead. Yep, inside loop, or like int I is equal to 0, I plus plus, blah, 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 blah. That's local to that scope. You can always limit, in fact, you should limit the scope of variables as much as possible. Yeah? So basically, like anything inside brackets, so like inside. Yep, exactly. Think of the curly brackets as a scope that you're looking through. And I can't curl my fingers too much. But now I've curled my fingers, and this is the scope. If I curl my fingers even more, and if I had 4 hands instead of 2, I could nest it, and then create another inner scope, right? Now the outer scope can still see everything inside that inner scope, I guess, no, sorry. The inner scope can see everything outside of its scope, but ultimately what you are doing is you are sequestering things into their own scope. And the curly brackets establish code blocks to do that in C. All right, we'll revisit this later on. What I want to do now is I want to simplify this code. Do you really need a variable? I create a variable, I put a value in it, and then I immediately return it. You can also return an expression. What if I just return what this is? Why use many words when few words do, right? Or whatever the quote is from Office, right? Why use 2 lines of code when you can get away with 1? And why create a variable when you don't need to, right? That's another acronym, KISS. Keep it simple, right? Stupid. All right. Oh, nope. I want to make sure that I'm still compiling. Oh, and then of course I need to get rid of this. There we go. I can't do that. And now it compiles. Okay. All right. So, other observations that we made. Prototypes end with a semicolon. Right? Don't repeat yourself principle. Right? Et cetera, et cetera. Okay. Yeah, and then the other observation that we made is that any variable declared inside of a function has a local scope. It only exists inside that function, not outside, nor in other functions. All right. There we go. Let's see. You use the keyword return to return a value or expression. And Yeah. Not only does our function provide new functionality, but it also illustrates code reuse itself. Did we start? So we didn't reinvent the wheel entirely, right? We made a better wheel. The wheel that was already created was the round function. We have a function calling another function. Maybe inside that round function, that function calls yet another function to do work for it, right? I don't know. I don't care because of procedural abstraction. I don't want to have to worry about those details. But I've illustrated code reuse at another fundamental level here. Why reinvent the wheel entirely when you can take a wheel and add some bells and whistles to it, and now you've got a new type of wheel that goes even faster, does even something different or better, right? Etc. So, what I want to do now is I want to create my own library. Right? So first of all, let's take a look at this. This is a pretty simple program, right? There's a main function, there's a round descents function. Maybe there's another optimization here. What about monthly payment? It's a really long line. It's pretty complicated. Maybe, I mean, we only use it once, so it's not screaming out to me to make a function for it, but it's pretty complex. Maybe I have use for it somewhere else in another program. So maybe we do have an argument here, even though we're only using it once, to create a function for it. So double, get monthly payment. Maybe if I just called it monthly payment, right? And I'll take the inputs here eventually. Is that a good name? Monthly payment. That sounds like a noun to me, right? So here's a trick. Again, there are only two difficult things in computer science: cache invalidation and naming things. So I don't like compute monthly payment. Well, usually we just write get monthly payment. That's a verb, right? And we're cheating now because we're offloading our creativity. I don't care. Just get it for me, please, right? And what do we need to compute that monthly payment? You remember? I think the annual rate. In fact, I could just cut and paste it here. The annual rate, which is a double. The principal, which is a double. And this also illustrates multiple variable, and then years, which is an integer, right? This also represents a multiple inputs, right? Here we're taking 3 inputs. The first 2 are doubles. The third one is an integer, right? What does it return? It returns a double, right? So, and add your documentation. This function computes the monthly payment of a loan based on that blah formula. I don't know who's responsible for it, but based on Euler's formula or whatever the hell it is, right? Business folks, do you know what it's called? Is there a fancy name for it? Nope. To-do, look that up later. Formula. Right? In fact, what you can do with doc-style comments is you can put in a hyperlink to a Wikipedia page that tells you all about how that formula is derived, right? And now that's in your documentation so that somebody can actually read it and where the heck did they get this magic formula? It's over there. I cited my work. Go check that out. I don't know, right? I don't know how it works. I just grabbed it off the internet. Right? Okay. Let's go ahead and implement it down here. So again, we replace the semicolon with a loop or with a function body, and then I'm going to go ahead and grab this piece of code right here, and cut and paste. I'm actually not cutting and pasting. I'm moving it. Return it down here, and then I'm going to use it up here. Get monthly payment of the annual rate, the principal, comma, and finally the number of years. There we go. The order matters, right? If I tried to go years, annual rate, principal, that's not what the function expects. The function expects 2 doubles, the first one being the annual rate and the second one being the principal. So just like printf, if you go out of order, right, you're going to get weird results. You can't go out of order here either. Okay? Let's see if this works or if I screwed up. Nope, it works. Right? This is getting kind of big though. Now I've got two functions. I think that that's pretty much it, right? Maybe reading the inputs, that could be put into a function. Maybe computing the monthly interest, that could be put into a function. My point is that eventually we're going to have complex enough programs that we have a dozen functions, 50 functions, 1,000 functions. Do you want them all in the same big giant file that's now millions of lines of code long? Right? We call those LOCs, by the way, lines of code. And if you're in a bad organization that rewards lines of code, right? Oh, this person is really productive. They wrote 10,000 lines of code last week, right? Thank you. I get my promotion. I get my bonus. I get my, right? That just incentivizes you to write longer and longer and longer code, right? The bad organizations do that. Bad organizations measure stuff in locks, lines of code. If you can write the same stuff with only 10 lines of code, probably okay. Now, if you can get it down to 1 line of code, you're probably being too clever. There is a fine line between being clever and being understandable. Right? You don't want to be too clever. You want to be more understandable. But of course, you don't want to blow it up to thousands and thousands of unnecessary lines of code. Right? You need to be Goldilocks about it. What did Goldilocks like? She didn't like the porridge that was too hot. She didn't like the porridge that was too cold. She liked it just right. Right? So you need to be Goldilocks about it. Right? All right. But I don't want everything to be in one giant file. So I want to start separating things out into different files. Okay? And to do that, we need to create our own libraries. Right? C does this right off the bat. The standard library stuff, that's in one file. The standard input-output library stuff, that's in a different file. The math stuff, that's in a third file. Right? And as you will see, the Boolean stuff, that's in yet another file. Separating things out into modules leads to a lot easier and modular code, separation of code, reduction of files, of sizes and stuff like that. Then you can bring in only what you need. So how do we do that? All right? So what I'm going to do is I'm going to show this by a demonstration. All right. What I'm going to do is I'm going to separate my code, my utility functions. Utility functions is just a generic term for functions that provide you functionality, provide you some utilities, right? It's like Batman's utility belt, right? He's got a bunch of stuff on there that's useful, right? It's a utility function, right? Separate my utility functions into different files, right? The prototypes will go into a header file with the extension .h. Boy, that looks familiar. Where have you seen .h before? The other libraries. stdio.h, stdlib.h. Those are header files. The definitions will go into source files with extensions .c. Right? You've seen that before too, right? Loan.c, right? So that's our source file. Somebody does point out that you can do. So there are actually a couple of contests with code. Of course, you can go into programming contests. We have several. Every year I think we send a programming team to internationals. If you're interested in that, they'll be advertising for new recruits so that you can join the competitive programming team here in our department, or now school, right? But also there are other games that you can play with code. One of them is called Code Golf, right? Here's a piece of code. Okay, I can get that down, that 5-line piece of code, I can get that down to 3. Or I can get that down to 1 line of code. Okay, well, I can too, but I'm going to have 10 characters on that line. I can do it with 8 characters. I can do it with 3 characters, right? Then it gets ridiculous. That's called Code Golf. Why? You're looking for the shortest, smallest piece of code that accomplishes something, right? Just like in golf, you're looking for the lowest score, the lowest number of strokes that you need to get it in the hole. Right? There's also the comment online points out that you can also join what are called obfuscated code contests, where you can make the most incomprehensible code, right? That nobody would be able to understand how it works. You have to really, really dig deep to find out how is this doing this, because it looks so weird. And you're obfuscating it, right? You're making it look completely incomprehensible, yet still functional, right? And so there are kind of there are contests and stuff like that all over the place, right? We want our code to be readable and understandable, though, right? This is not a contest, right? This is something else. So the definitions will go into source files, all right? So let me go ahead and go through that process, and then I'm going to show you how to compile it. So first of all, I need another file. Let me go ahead and go over here and go new file. I'm just going to call it generically utils.h. That's the header file. And I'm going to also go ahead and create another file, the source file, called utils.c. Okay? Question? Yeah, go ahead.
So, looking at those we also include utils?
Eventually, yes. But I need to separate them first. So I'm going to take all those prototypes, cut, paste, and I'm going to put it in the header file over here. Okay? I'm going to go back and all of those definitions down below, I'm going to go ahead and put those into the source file over here. Now, remember, you have to declare a function before you can use it. So technically, what do I need to do in this file? Do you see any prototypes here at all? I need to bring them in. I need to include them. So, include, we've seen that before, but instead of langle-wrangle of stdio.h, right? What we're going to do is we're going to use a double quote, utils.h. And I'll describe why here in a second. You can get away with langle-wrangle, but it's bad practice because you're basically saying, my library is a standard library. And this ain't a standard library. Right? This is my library. Okay? All right, let's go back over to loans here. I see that we're using get monthly payment and round to cents, but do you see the prototypes anymore? Nope. So what we need to do is we need to bring those in by including our header file. Now, the dirty secret about a preprocessor directive is that it is literally a cut and paste operation. The preprocessor, not the compiler, the preprocessor goes in, opens up this file, sees all of the, and does a cut and paste of all of these prototypes, and comes over here and pastes it right here, replaces this with all those prototypes, what I had before. Right? But it does it for us so that we don't have to have all that junk in, all that extra stuff in this file. Right? We can separate it out into another file and not have to worry about it. Right? Imagine if we didn't have that. Every single prototype in the standard library, every single prototype in the input-output library, every single prototype in the math library and in our own library, we would have to go and cut and paste all those things and bring them in and paste them into our file, making it thousands or millions of lines of code long. Right? Not good. Right? All right, so let me go ahead and try to compile this now. Doesn't work. Right? For the same reason as before, undefined reference, undefined reference. It knows about them because we're bringing in that header file. It knows that there's this function called get monthly payment. It knows that there's this function called round to cents. It doesn't know where they are to link them in, just like if we had left off the -lm flag. Right? Now it doesn't know what anything is. Right? So hyphen utils, right? Or hyphen you link in that utils library right there. That's not going to work either because it doesn't know what utils is. Okay? What I have to do is I have to compile it into a library. So gcc-c utils.c. Does anybody remember on probably day 2 what the -c flag does? Remember I gave you this demonstration where we went from C code into assembly code into machine code? Oops. Well, that's something else here. By the way, let's go back over here to this. And what else do we need to include? Because I'm using round and pow. Include the math library here. There we go. There. What did I just do? The C stands for what? Compile, right? Compile, but do not link. Do you see over here there's something new that just popped up? This .o file, right? What is that thing? Yeah, it's an object file. If I double click on this, probably not going to let me double click on this. No, because it's a binary file. I can go ahead and try to force it to. Yep, it's not a text file. Okay, fine, right? If I tried to look at it, I'm sure that I would, less, utils, oh, yes, there. Garbage, 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 right? And not garbage, but machine code, right? It's not something that we can read and comprehend anymore. So that's an object file. Somewhere on the system, there's a math.o file, right? And that's when you use the -lm, it's bringing in that object file to link everything together to actually build an a.out file, right? So how do we bring in our library? GCC, what was it, loan, right? Loan.c, -lm brings in the math library. Utils.o says, also include that object file because you're going to need it, because round to cents and get monthly payment are in there too. Oops. The order matters here. I think utils.o. This is Ubuntu, being Ubuntu. There we go. LM has to be the last thing. That's Ubuntu, right? So a.out, we have the exact same behavior as before. All right, fine, whatever, $10,000. There we go, $10,000, 5%, and 5 years. Much, much cleaner, right? Not only that, but I've taken code reuse to the next level. This utils library, right? It has round to cents. It has get monthly payment. I could put a whole bunch of financial stuff into this utility library. And now I could publish that as another library. Like, all right, there's all these financial utility functions that you can use. You can use it in that program over there, that program over there, that program over there, just like the math functions, right? You can use a square root function in 50 different programs if you want, but you can only do it because it was put into a separate library that you can then link in. Yeah? Good question. Then you have to set up a class path. I don't remember how to do that off the top of my head. That's why you write what are called make files. And so anytime I have to do that, I look up the documentation again for how do I do that in a make file again. I write the make file, I push it to GitHub, you all use it, and then I forget how I did it. Question? You had a question too?
So basically, for like get monthly payment, if we change the variable a little bit, like the name of it, will it still
Nope. So let's go ahead and change it, the header file. Now let's try to compile that file. Right? It's going to wonder, well, that's going to work. But when I go to compile everything else, it only works because it thinks that there's this round to cents and this monthly payment. It has no idea where to actually find that because it's a different name over here. Right? And so when I actually try to compile this, as before, I didn't find any monthly payment. Right? It would be like misspelling the square root function. Right? So let's undo that and make sure that they, oops, .h. I needed to undo it over here. There we go. Right. So it compiled this way because it said, okay, I guess I'll find that monthly payment somewhere else. You'll provide it in yet another library, right? And so it's happy to compile it because that's not my problem. That's another library's problem. Right? Other questions? Okay, then let's review what we just did. You separate the prototypes into a header file. You separate the definitions into a source file with the extension .c, but generally, the same base file name. You note that I named it utils.h and utils.c. If I had named them something different, that would have been super weird, right? My awesome utils.h and my slightly less than awesome utils.c, right? Those don't match. You want to make sure that they match. They don't have to match, but it's organization thing, right? What else? You compile the library files into an object file using, and the command that I used was gcc -c utils.c, right? This produces an object file, utils.o, right? You compile the entire program into an executable using gcc, what was loan.c was the example, utils.o, and then -lm at the end. Again, the -lm at the end for Ubuntu /CS50 IDE. Your mileage may vary if you use a different operating system. Like CSE, that -lm does not have to be at the end. In fact, I don't think it can be at the end. It has to be somewhere else. Again, your mileage may vary, right? Why? What is that? Why your mileage may vary? There we go. All right. All right. Questions on that so far? Otherwise, we're going to get a lot more practice as we move along, especially next week in your lab. You're going to be taking some utility functions that deal with colors, RGB values, CMYK values, and ultimately you're going to be building this image library of utilities for manipulating images. And then you'll be able to, do a sepia tone image. Take an image, take it and put it through a filter like sepia or through a black and white filter, or flip it, right? Reverse the image, do a bunch of different image manipulation stuff with the libraries that you build eventually. Okay. All right. So Oklahoma to cover. All right. Nobody cares about football apparently. All right. I'll see you next week.